Dear students, now I'm going to teach a problem in radiation, particularly in the problem related to basic law of radiations. So, what are the basic laws that are available in the radiation? This is easily find in the HMT data book in the column radiation chapter. We can find easily what are the laws available. So, first law, that is the Kirchhoff law. In Kirchhoff law, the emissivity of the body, that is equal directly proportional to absorptivity of the body at a particular wavelength. Then second law, that is the Wien's displacement law or Wien's law. So which is especially for finding the relationship between the wavelength and temperature. So at particular temperature, what is the maximum wavelength? That is, what is the wavelength which emit the maximum emissive power? So this can be seen in the next slide. Otherwise, I can see we can discuss here also. So one that is called as that is monochromatic emissive power E lambda of B. That is a wavelength. This is a graph in action by axis. Here we having some temperature lines. This temperature is line for 1000 Kelvin, and this temperature line is for 1500 Kelvin, and this temperature line is for 2000 Kelvin, and this temperature line is for 3000 Kelvin. 3000 Kelvin, 2000. It is a 1500. It is a 1000. So for each temperature line, we attain the temperature maybe attains some peaks. So what is the peaks? So for the 3000 Kelvin temperature line, attain that peak. The wavelength at the particular peak is nothing but lambda max. So for 3000 Kelvin, we have some peak. The wavelength corresponding to the peak is nothing but lambda max. So at that point, the emissive power is maximum. So Wien's law deals a relationship between the at which wavelength, that is called lambda max, for the given temperature, which gives the maximum emissive, that is called as that is constant. So lambda max into T is equal to constant. That constant is nothing but 2898 micrometer Kelvin. Then third law, that is called as Stephen Boltzmann's law. So EB is equal to sigma T power 4. This law is mainly used for finding what is the emissive power of the particular body having a temperature. If a body is having a sun which is in spherical shape, that having a sun temperature of 5000 Kelvin, what is the maximum emissive power that emitted by the sun? So for this case of problem, we are using Stephen Boltzmann's law. If the emissivity of the surfaces and area of the surface is given, the Stephen Boltzmann's law can be elaborated as epsilon A sigma T to the power of 4. So instead of sigma T to the power of 4, we are introducing another constant, some constant, that is emissivity and area. So emissivity, that is defined as the emissivity is equal to emissive power of the given body divided by emissive power of the black body. Area is equal to what is the surface area of the radiation that is emitted. So for calculating emissive power, Stephen Boltzmann's law is used. The next law is called as a Planck's law. The Planck's law is also used to find the emissive power at given wavelength. It is not a maximum at a given wavelength. So Wien's displacement law deals with the maximum emissive power. So here that is at a maximum emissive power, what is the wavelength that deals with the Wien's displacement law. But in a Planck's law, for a wavelength, say for this particular wavelength, for a given temperature, what is the emissive power? So this can be calculated with the help of Planck's law. So Wien's law deals with the wavelength, the corresponding wavelength for which the emissive power is maximum. But in Planck's law deals with at a particular temperature for a particular wavelength, what is the emissive power? There is a fourth one. Then these four laws are basically used. Then next one, that is Stephen Boltzmann constant sigma is equal to 5.600 to the power of 8 watt per meter square Kelvin. So these are the four laws. I think in the Planck's law we have some constant, that is a C1 and C2. So C1, that is given in terms of 0.734 into 10 to the power of watt per meter square, and C2, this constant is 0.01438 meter Kelvin. So these two constants are substituted in Planck's law to find the emissive power at particular wavelength. Okay, now we move to the problem. Okay, in the problem, for a spherical ball, it's having one spherical ball. Then spherical ball, as that is nothing but we call it, that is called as a black body. So you know, black body, which is the body that whatever the radiation that absorbed is emitted back, 100% emitted back. So that body is called as a black body. So black body having emissivity that is equal to 1, emitting radiation at a temperature of 2500 degrees Celsius, which is equal to 2500 plus 273, which is equal to temperature 2773 Kelvin. Please note that in radiation, the temperature should be substituted in terms of Kelvin, not in a degree Celsius. Okay. Then first one, we're going to find monochromatic emissive power. Okay. First one, monochromatic emissive given wavelength. Already I told the wavelength is given and the temperature is given. What is the formula to find emissive power? That formula is not called as, that is the Planck's law. That law is called the Planck's law, Planck's formula. So Planck's formula, that is the first one, that is a E lambda B, which is equal to C1 lambda power minus 5 divided by the expression of C2 divided by lambda T minus 1. So again we see the formula that C1 lambda power minus 5 expression of C2 by lambda T minus 1. Okay, C1 and C2 are the constants, we noted. Here the C1, that which is equal to 0.3742 into 10 to the power of minus 15 into lambda, that is equal to 1.2 micrometer. So here the wavelength lambda 1.2 micrometer again converted into 1.2 into 10 to the power of minus 6 meter. So lambda can be substituted in meter instead of micrometer. So 10 to the power of minus 6 whole power 5. Then e power, that is C2 having a constant, that is 1.4388 into 10 to the power of minus 2. But in data bit can be represented 0.001 into 10 to the power of minus 6 something, divided by lambda, that is 1.2 into 10 to the power of minus 6 into temperature 2773 minus 1. So after substituting the values, you are getting monochromatic emissive power at given wavelength and temperature, which is equal to 2.014 into 10 to the power of 12 watt per meter square. So this emissive power which is equal to, at the condition is, so at 2773 Kelvin and temperature, that is called as a lambda, and temperature is that is called as a temperature, and lambda, which is equal to 1.2 micrometer. So for this condition, we can draw the one curve. So that curve, it is a lambda, that is E lambda B. We having the temperature line. So this is the temperature line for 2773 Kelvin at a wavelength of say 1 micrometer. So 1.2 at a wavelength of 1.2 micrometer, we are getting the E lambda B. So this E lambda B is equal to, what you get is 2.014 10 to the power of 12 watt per meter Kelvin at the temperature of, at the wavelength of 1.2 micrometer and temperature of 2773 Kelvin. So please note that at a particular temperature and particular wavelength, you are going to find the emissive power. At that place, we are using a Planck's law. Then second one, you are going to find wavelength at which the emission is maximum. Okay. Now we can discuss the same problem here. So this is a 2773 Kelvin. That is E lambda. So at which point you are getting the maximum emissive? This is the point we are getting the maximum emissive. That is the point rating. That is the E lambda B maximum. Then the corresponding wavelength. So this corresponding wavelength we call it as, that is called as a lambda max. It is not a maximum wavelength. Wavelength at which the maximum emissive power is obtained. That is called as a lambda max. Don't confuse with the lambda max. It is the max at which lambda we are getting the maximum emissive power. That we call as a lambda max. So we are going to find the temperature at that point. Now we are using, that is the Wien's law, Wien's displacement law or Wien's law. Here this can be found, that is a lambda max into T is equal to, that is called as a constant. Well, lambda max into T already you know, that is a T is equal to 277 Kelvin. If constant is equal to, here constant is equal to 2898 micrometer. I think some issue, that micrometer Kelvin. So here lambda max is equal to 2898 divided by, what is the temperature? 2773. We are getting lambda max is equal to 1.045 micrometer. So not getting clearly 1.0. Some issues is that. So lambda max is equal to 1.045. So this lambda max is equal to 1.045 micrometer. So this is the point we are getting maximum emissive power. Okay. Then third one, we are going to find maximum emissive power. First one is the monochromatic emissive power. The next one is the maximum emissive power. So maximum emissive power is calculated by the formula. One formula, that is a E lambda into B. That is, sorry, E lambda B. B is present. Max is equal to 1.285 into 10 to the power of minus 5 T to the power of 5. That is watt per meter square per meter length. You note that the unit for the emissive power is given here. That is E lambda B. It is equal to watt per meter square micrometer. That is equal to how much amount of power that is emitted per meter square per unit wavelength. Per unit wavelength. So at particular wavelength, what is the emissive power? So that is the given. So watt per meter square per meter length. Okay. Here you know the temperature value 1.2 into power of 5. What is the temperature? 2773 whole power 5. So here E lambda B max, which is equal to, we are getting the 2.1 into 10 to the power of 12 watt per meter square per meter length. Okay. The next one, fifth one, we are going to find, sorry, fourth one you are going to find, that is total emissive power in watt per meter square. So already you know, so that is emissive power. So emissive power can be calculated by means of, that is called as a Stephen-Boltzmann's law. Stephen-Boltzmann's law, that is already known from the data book. That is EB is equal to EB is directly proportional to T power 5. By replacing constant proportionality, EB is equal to sigma T to the power of 4. So sigma you already know constant, that is Stephen-Boltzmann 5.600 to the power of 8 watt per meter square Kelvin power 4 into temperature, that is a 2773 Kelvin power 4. After substituting the values, you are getting the emissive power, total emissive power is equal to, that is a 3.352 to 10 to the power of 6 watt per meter square. Okay. The next one, it's fine to find, that is the total emissive power. Next one is total emissive power if the ball is assumed as a real surface with emissivity is equal to 0.9. Here, the same ball, the spherical ball that's having emissivity, some issues in that area. So, spherical ball having emissivity of 0.9. This can be again calculated by means of Stephen Boltzmann's law, emissive power which is equal to sigma T to the power of 4. If emissivity is given, EB is equal to epsilon into sigma T to the power of 4. So epsilon that is equal to given, that is called as emissivity. Emissivity is equal to emissive power of the given body divided by emissive power of the black body. Already we know black body having a emissivity which is equal to 1 because the emissive power is maximum for a black body, because what are the rays that absorbed by the black body that is again emitted back. So it completely absorbs all the incident radiation and it's completely emitted. So that's why it's having a maximum emissive power. So epsilon that is equal to given 0.9 into sigma 5.67 into 10 to the power of minus 8 into 2773. So finally, you are getting AB, which is equal to that is 3.352 into 10 to the power of 6 watt per meter square. Okay. Then last one, the same problem with emissive power if the spherical ball having some diameter. So diameter is equal to 10 power of 9 meter. If the fit is 10 to the power of 9 meter, how much amount of radiation is emitted? Here it is per unit area, here also per unit area, but here it is for the entire system. So here EB is equal to sigma T to the power of 4. If emissivity is given, EB is equal to epsilon sigma T to the power of 4. If area is diameter or something is given, EB is equal to A into epsilon into sigma T to the power of 4. You already know sigma T2 that is found in the previous problem. Here that is a sphere. The surface area of the sphere is equal to 4 pi r square. That is equal to what? Pi d square. Pi d square into that value, this sigma T to the power of this value is coming here. That is equal to 3.352 into 10 to the power of 6. So diameter you already know that is equal to pi into 10 to the power of 9 into that same value. So here that is after the substituting this value, wait, pi into 10 to the power of 9 whole square into 3.352 into 10 to the power of 6. You're almost getting the value which is equal to 1.053. So approximately which is equal to 1.0530 into 10 to the power of, that is equal to 25 watt. So that is EB. So you consider you are having a 3 EBs. Sorry, you have a 3 EBs. So one is emissive power for, that is the emissivity is equal to 1. Here the emissivity is different, that is 0.9. Here if the area is given, it is the, this is the total emissivity that can be represented by watt, but again the other two represented as a watt per meter square Kelvin. Okay. Then again we solve some other basic problems that are related to the radiation also. This is a continuation with the similar to the previous problem. Okay. Here this assuming the sun is to be a black body, it is observed that the intensity of the radiation emitted by the sun is maximum at a wavelength of 0.49 micrometer. So sun is to be a black body, so emissivity is equal to 1 because it is given as, that is called as a black body. It emits the radiation and it emits the maximum, the intensity of the radiation emitted by the sun is maximum at a wavelength of 0.49 micrometer. So E lambda B is equal to maximum at 0.49 micrometer. Already we studied the law which relates the lambda max and temperature. That law is called as Wien's displacements law. Wien's displacements law that relates the lambda max and temperature. Here, as per the law, that is the lambda max into T is equal to 2898 micrometer Kelvin. So lambda max already given. Again, I am saying there is not a lambda max. It is a lambda at which the emissive power is maximum. So for this, we call it as at maximum wavelength. So that's why at maximum wavelength we call it as a lambda max. So at a wavelength of 0.49 micrometer, better we convert. This is also in micrometer, so we can. This is also micrometer Kelvin. So better use this 0.49 into temperature is equal to 28 micrometer Kelvin. So from that substitution, we may get the temperature which is equal to 5914 Kelvin. Then second one, we are going to find that is a temperature. You find what? Then second one, estimate the surface temperature we may find. Then second one, that is equal to MC power. So already you know the MC power can be determined from the Stephen Boltzmann's law. Sigma is directly equals to T to the power 4. So by replacing constant power is sigma T to the power 4. So sigma you may know that is 5.67 into 10 to the power of 58 watt per meter square Kelvin power 4. That is the Stephen Boltzmann constant. Temperature we already find, that is equal to 5914 Kelvin whole power 4. So after substituting these values, we are getting that emissive power which is equal to 6.9, I think 6.9 into 10 to the power of 7 watt per meter square. Okay, so these two are the final result of this problem. Okay, I'm sorry I'm on till one thing in the previous problem here. In this previous condition, you note that epsilon is equal to emissive power of the given body. So epsilon is equal to, sorry, I am right here. Epsilon is equal to emissive power of the given body divided by emissive power of the black body. If black body is given, it is which is called as emissivity is 1. So for a real body, the emissivity is less than 1. So this is the condition. We can call it as a gray body or real body. Here the emissivity, sorry, wait, this is area, gray body, real body with area. This one is the gray body because the emissivity is given, gray body or real body. This is the black body because the emissivity is equal to 1. You can substitute this value, that is for a gray body that is given, there is a 3.352 into 10 to the power of 6 divided by for black body, that is equal to 3. Sorry, this value that may be slightly different from the previous one. 3.017, sorry, 3.017. So 3.017 into 10 to the power 3.352 into 10 to the power of 6. So by dividing this two, we are getting almost the value that is a 0.009 something. That is called as emissivity. This emissivity goes to this, that is 0.9. Okay, so I made a mistake in this previous one, which is equal to 3.017 to the power of 6 watt per meter square. Okay, now we can move to the third one. This is another one basic problem. The body is a capital temperature of 827 degrees Celsius. Estimate the thermal radiation emitted by the fragment between 1 and 5 micrometer wavelength, isn't? So here that is E lambda B, it is called lambda. Okay, the unit is micrometer, it is equal to watt per meter square per meter length. Here the temperature is equal to T is equal to 827 degrees Celsius. For converting into Kelvin, 827 plus 273, 1100 Kelvin. So 1100 Kelvin having a temperature profile is like this. So T is equal to 1100 Kelvin. Here we need the energy emitted by the fraction that is equal to 1 micrometer to that is a 5 micrometer. So this is the area we are going to calculate. So how we can calculate this area? So this can be calculated by the standard procedure which is available in the data book. Okay. So in a data book, please note that in a data book this is a given. So here lambda T micrometer Kelvin. For that we are having a value that is equal to EB0 to lambda sigma T to the power of 4. How we can how we can taken from the problem? Listen. So this is calculated by, so I think this is 0. This is again calculated. So from 0 to you can find this value. There is a 0 to 5 micrometer. In that you can substitute 0 to 1 micrometer. First you find 0 to 5 micrometer, then you can find 0 to 1 micrometer. A difference between these two terms is give 1 to 5 micrometer. So this is the area we are going to find. So this value that is available in the data book. So for that, first step we required is you have to find the lambda 1 into T. So lambda 1 into T. So lambda 1 which is equal to 1 micrometer. So 1 into temperature is equal to 1100 Kelvin. 1 micrometer into 1100 Kelvin. Finally, we are getting lambda 1 into T which is equal to 2200 micrometer Kelvin. Then again lambda 2 into T is equal to lambda 2 which is equal to 5 micrometer. Lambda 1 is equal to, here note that lambda 1 is equal to 1 micrometer. Lambda 2 is equal to 5 micrometer. So 5 into temperature 1100 Kelvin. So lambda 2 into T is equal to what into, so sorry, you can take, and this is, so we can take, this is a 2 micrometer, then 6 micrometer. We taken as a 2 micrometer and 6 micrometer. We can 2 that is equal to 2200 Kelvin. Sorry, 2200 because 2200 Kelvin. So it is a 6 micrometer. In a problem, you can consider as a 6. Lambda 2 is 6. This is 1. So you can consider this is a 6. Then this is a 2. Sorry, this is a 2. We need a 2 to 6 micrometer. Okay, this is a 2. This is a 6. So 6 into 1100 we are getting, that is a 6600 micrometer Kelvin. So lambda 1T and lambda 2T we already find. So from the lambda 1T, lambda 2T we are getting this value. Lambda 1T that is equal to what? This is a 2200. The EB0 of lambda by sigma T to the power of 0.1.0088. Then it again for 6600. So this is the at condition 1. At condition 2, 6600. we are getting 0.783199. We can note at the condition 1 and 2. Now we can write in the presentation. Here at this condition, here note that, so EB that is EB that is EB0, better we take it from the data book, EB0 to lambda divided by sigma t to the power 4. EB0 to lambda EB0 to lambda sigma divided by sigma t to the power of 4, which is equal to, that is 0.1 triple double 0, so 0.1 double 0 triple 8. Then at EB0 to lambda divided by sigma t to the power of 4 at the lambda t condition is equal to 0.783199. I think that 100,888. 100,888. Okay. Here. Okay. Now we are going to find this value from 0 to 6 and 0 to 6 minus of 0 to 2, we are getting, that is a 2 to 6. Okay. So substituting this condition, okay, you can find that is amount of radiation, how much amount of fraction of radiation that is to be emitted. Then the fraction of radiation emitted can be written as, that is f of 0 to lambda 1 into t, 0 to lambda 1 into t, which is equal to EB of 0 into lambda 1 into t divided by sigma t to the power of 4. Then f of 0 to lambda 2 into t is equal to EB of 0 sigma lambda 2 divided by t to the power 4. Simply, this equation is written as per the book, but for our convenience, we can substitute the values between. So we can consider this as a equation A. This is the equation B. We can substitute, that is a B minus A. B minus A. Simply, we written as EB of 0 lambda 2t minus EB of 0 lambda 1 into t divided by sigma t to the power of 4 is equal to, I have some issues there. So write the below, which is equal to 0.783199. Here 199, the value is missing there. 199 minus of 0.100,888. Okay, we can go to the next page. Sorry. Fine. We can have some values. So finally, EB of, that is a lambda 2 to lambda 1 divided by sigma t to the 4. After the subtraction, we are getting that value is equal to 0.6334. Then we are reading the fraction of radiation. You can neglect this one. This may be confusing. CB of lambda 2 to lambda 1 is equal to 0.6334 into sigma t to the power of 4. Already you know sigma, that is equal to Stephen Boltzmann constant. T power 4 is equal to T. Already you know the temperature is equal to 827, which is equal to 1100 Kelvin. So after substituting the sigma and T to the 4 in the equation, we are getting the fraction of, I have some issues in the space. So here I can write the fraction of radiation from the lambda 2 to lambda 1, which is equal to this multiplication of this value, you can get that may be around 35.9 kilowatt per meter square. So this is the value, that is a 35.9 kilowatt per meter square. So this is the between this 2 micrometer wavelength to 6 micrometer wavelength, we are getting the emissive power is 35.9 kilowatt per meter square. Okay, thank you. This in this last problem, so neglect this one because this may be confusing. So better from this range to this range minus this range, we are getting what is the area we can get. So in data book that is given here is divided by sigma T2 to the power 4. You can multiply sigma T2 to the power 4 in this equation. So what are the value you are getting into sigma T2 to the power we are getting, that is what is the emissive power in the particular wavelength. Okay, thank you.